Okay, so moving on, we are going to be talking about cryptographic hashing. Now, while the word cryptographic is in the term cryptographic hashing, and it does lead you to believe that there is encryption involved, there is no encryption involved in a cryptographic hash. There is a significant difference between hashing and any sort of encryption, and that is primarily that encryption is a two-way process. When I encrypt a piece of data or a file or anything else, what I'm doing is putting it into a state where I expect it to be able to get it back out again. In other words, when I encrypt a file, I expect it to be able to decrypt the file and get the original contents. Hashing is a one-way function on the other hand. Once I've hashed a piece of data or a file, there is no expectation and ability to get the original piece of data back. Hashing generates a fixed length value, and different types of hashing will generate different length values. For example, MD5 will generate a different length value than SHA-1, and they're both hashing algorithms, but they generate different length values. And the resulting value from a hash function should be in no relation at all to the original piece of data. As a matter of fact, if two inputs generate the same hash value, it's called a collision. And if you can generate collisions, you may be able to get a point where you can generate a piece of data that are going to generate the same hash values, and that leads you to the potential ability to break the particular hashing algorithm that you're using. So what we can use hash is for, well, one thing we can use hash is for file integrity. We can run a hash on a file and get a value back, and later we can check that the value to make sure if it's the same. If it's the same, I can be sure that the same file was hashed in both instances. So let me just show you an example of what I just said, that if we hash a file, we'll get the same hash every time. So remember the certificate that we just created. Let me just log in again. So we are going to hash this certificate, and it will create a certain hash. And we are going to see that every time we hash it, we are getting the same hash. So we can use this command called MD5 sum, and we can do edureka.crt. So this is the hash produced after you've hashed edureka.crt. So if I do an MD5 again, so MD5 is a hashing algorithm that you should know of. So edureka.crt, and it will produce very similar hash. Let's see if SHA-1 works like this. So SHA-1 edureka.crt. Okay, SHA-1 is the SHA from the SHA-utils package. Okay, so I've proved my point that with MD5, which is a cryptographic hashing algorithm, we are getting the same hash back. So if you are able to produce the same hash, that means you have broken the algorithm in itself. So if you run MD5 on Linux, you can get a version of MD5 and MD5 summation program on Windows and Mac OS, where with the utility MD5, which does the same thing. So I just showed you the file and I hashed it. And another reason we use hashing is we are storing passwords. So passwords are stored after hashing. We hash the passwords, and the reason for hashing passwords is so you're not storing the password in clear text, which would be easily seen even if you got it protected with permissions. If I hash the password every time I hash that password, I'm going to get the same value back from the same algorithm. So what I do is store the hash in some sort of password database. Since it's a one-way function, you can't get the password back directly from the hash. Now, what you can do with most password cracking programs, do some variation of this, and you just generate hashes against a list of words until you get a hash value that matches the one in the password. Once you get the hash that matches the one in the password, you know what password is there and here. And we come back to the idea of collisions. If I can take two different strings of characters and get the same values back, then it's easier to crack the password, because I may not necessarily get the password, but if the hash that I get back from a particular string of data is the same as that I get from the original password, then it doesn't matter whether I know the password, because the string of data that I put in is going to generate the same hash value that you're going to compare when you log in. And this hash value will just give you that it's valid, and you'll be able to log in. So suppose the password that you chose while making your account is dog, and the dog word produces this hash value. And if I were to like hash cat with the same algorithm, and if the algorithm was prone to collisions, it might produce the same hash value as dog. So with the password cat, I could open up your password. I could open up your account. So that was all about hashing and hashing algorithms. Let's move on now. Okay, so in this part of the video, we're going to go over SSL and TLS. Now, SSL and TLS are ways of doing encryption, and they were developed in order to do encryption between websites, web servers, and clients or browsers. SSL was originally developed by a company called Netscape. And if you don't remember, Netscape eventually spun off their source code and became Mozilla Project, where we get Firefox from. So back in 1995, Netscape released a version 2 of SSL, and there was a version 1, but nothing was ever done with it. So we got to version 2 of SSL, and that was used for encryption of web transmission between the server and the browser to do a whole number of flaws between the server and the browser. Now, SSL version 2 had a whole number of flaws, and SSL 2 has the type of flaws that can lead to decryption of messages without actually having the correct keys and not being the right endpoints. And so Netscape released SSL version 3 in 1996. And so we get SSL 3.0, which is better than 2.0, but it still had some issues. And so in 1999, we ended up with TLS. Now, SSL is secure socket layer and TLS is transport layer security. They both accomplish the same sort of thing, and they're designed for primarily doing encryption between web server and web browsers because we want to be able to encrypt the type of traffic. So let me show you what kind of traffic looks like. So first of all, let me open Wireshark. And out here, I already have a TLS scan ready for you guys that you can see we have all sorts of TLS data. So you can see that here's my source and it's 1.32 and destination is 7612.4059.46, doing a client key exchange and the change cipher spec and an encrypted handshake message. And then we start getting application data. So there are some other steps involved here, and you're not seeing all of it with this particular Wireshark capture because, again, we get fragmented packets, and at some point it starts getting encrypted. And you can't see it anyways because Wireshark, without having the key, can't decrypt those messages. But what ends up happening is the client sends a hello, and the server responds with a hello, and they end up exchanging information as a part of that. Now, including version numbers supported, and you get random number, and the client's going to send out a number of cipher suits that may want to support an order, and it can support the server, and it's going to pick from those suite of ciphers. Now, then we start doing the key exchange and then do the change cipher spec and from the client and server, and eventually the server just sends a finished message. And at the point we've got this encrypted communication going on, but there's this handshake that goes on between the two systems. And there's a number of different types of handshakes depending on the type of endpoints that you've got. But that's the type of communication that goes on between servers and the client one. Important thing about using SSL and TLS is, as I mentioned, some of the earlier versions had vulnerabilities in them, and you want to make sure that the servers aren't actually running those. So you want to run some scans to figure out the type of calls and ciphers that different systems use. So for this, we can use something called SSL scan. So this is available for Unix. I'm not really sure if there is something that is similar for Windows or Mac, but on a Unix-based system that is Linux, we can use SSL scan. So let me just show you how to use that. Clear this part out. So what we can do is run SSL scan again, suppose www.edureka.co. So I'm going to do an SSL scan here against the website, and you can see it's going out and probing all the different types of ciphers that we know on this system. Start with SSL v3 and are going to TLS version 1. And we could force SSL scan to try to do an SSL v2 if I scroll back up. Here I get the surface ciphers, which is SSL version 3. It's using RSA, and it's using RSA for the asymmetric. Now, in order to do the key exchange, and once we get the session key up, we're going to use AES 256, and then we're going to use the secure hash algorithm to do the message authentication, or the MAC. It's sometimes called the HMAC for the hashed message authentication code. And what it does is simply hashes the MAC address that you would check one side against the other to make sure that the message hasn't been fiddled with in transmission. You can see here all the different types of cipher suits that are available. Here's TLS running RC4 at 40 bits using MD5, so that would be a pretty vulnerable type of communication to use. And between the server and the client, a 40-bit cipher using RC4 is a low-strength cipher, and we would definitely recommend that clients remove those from the supported ciphers that they have on their server. All that configuration would be done at the web server as well as when you generated your key and your certificates. Normally, certificates would be handled by a certificate authority. Now, you can also self-sign certificates and have those installed in your web server in order to do communications with your clients. The challenge with that is browsers today warn when they see a certificate against a certificate authority that is entrusted of it, and it doesn't have any certificate authority at all. So you'll get a warning in your browser indicating there may be a problem with your certificate if your clients are savvy enough. And if the users are savvy enough, you may be able to make use of these self-signed certificates and save yourself some money. But generally, it's not recommended simply because clients are starting to get these bad certificates. And when they run across one that's really a problem, a real rogue certificate, they're going to ignore the certificate message in their browser and just go to these sites that could have malicious purposes in mind and may end up compromising the clients or your customers or users. So that's SSL and TLS and how they work and negotiate between servers and endpoints.